from Adrian, Adrian Roellin from Singapore, and he will talk about higher order fluctuations in dense random graph models.
Thank you very much. Well, first, thanks to the organizers, Christian, Remco, Subik, and Sophia for the kind invitation, and it's been a great workshop so far. So I've added this subtitle, statistical aspects, to the title because I realized that Gaussian, who's on this project as well, she was going to talk about the same thing. So I will therefore focus a little bit more on follow-up work with my PhD student, Li Shang, and which goes more into the statistical parts of this, whereas Gaussian will focus more on the mathematical distributional limit part of the project. So let me quickly talk a little bit. I mean, this is mostly just notation because most of us here, or all of us here, know about these things. So we have G1, G2, and so on and so forth, a dense graph sequence, and we'll fix F, denote that as the F we're counting the subgraph density of which we're interested in. And the subgraph density here again is injective homomorphisms. We are not looking at induced subgraphs, just at regular subgraph counts, and that'll be the notation here, T sub F of Gn. The usual model we're looking at, the workhorse of dense graph limit theorem is limit theory, is we fix the graph on kappa. I've realized there's various traditions in the community what letter we should use. As a probabilist, I'm hesitant to use a capital W for that because it's sort of, I don't want to waste letters on things that are not random. So I use kappa for that. That's more in the tradition of Bolobosch and Riordan. I think they've introduced that in their paper, so I stick to that. U1, UN, up to UN, I add the uniforms. That'll be the vertex labels. And we connect the vertices I and j with probability kappa uij. And then will be UN kappa is this random graph. And of course, the cornerstone of the theory, one of the cornerstones is this law of large numbers, which says that this random graph sequence converges in this in the metric space of graphons to back to the original kappa that we started with, and that is can be expressed in terms of the subgraph densities converging to this deterministic quantity. So as a probabilist, once you give me a law of large numbers, I will ask the question, well, what's the central limit theorem of that? So we are asking about fluctuations of subgraph densities as a next step in this endeavor. What's the central limit theorem of dense graph limit theory? And it's not quite clear, or at least wasn't for a while. So here's a discouraging observation. You take an Addish-Renyi random graph, so P now, so kappa is just P, constant. You observe the following. These subgraph densities are perfectly correlated in the limit, okay? And they all correlate with the edge density. So in that sense, it's discouraging because it's telling us all the fluctuations are essentially the same. They're governed by the edge densities. If you have more edges, you will have more triangles. You will have more 4 cycles because we're in the dense case. So that's ultimately a reason. So that's that. So if you wish, you can stop here and say, well, that's the central limit theorem of random dense graph limit theory. This object here, the randomness is just a sum of independent Bernoullis. They're not IID because the graph one need not be constant. In this case, it is. So in this case, just binomial distribution. In general, it need not be. Okay, for general graphons, it's a bit more complicated. There is not one source of randomness that governs the whole thing. So in general, we'll have that these subgraph densities are dominated by functions, by sums of this form. So you take your labels, you take functions of these labels, which depend on F, which can depend on kappa, and those are the objects that will dominate. So the correlation need not be one anymore because the G's can differ for different F's. But the observation is that fluctuations of subgraph densities are essentially dominated by the vertex label. And I think Bashwar, where is he? Oh, there, thank you. Yesterday's talk mentioned this. That's the sort of, that's the source of the randomness that we're observing most in general is just the vertex labels. I say in general here because his talk was about coming up with conditions, these regularity conditions under which there are the randomness as observed, sources of randomness. But in general, if you give me a random graphon, if you will, that'll be the situation. Well, that's sort of disappointing because if we do statistical testing, what are we testing actually, right? So at the end of the day, we want to test edges, connectivity. We don't want to test vertex labels. So that's sort of, in some sense, disappointing that this is the case. But so there's this work by Janson and Nowitzki from the 90s, and then there was a big monograph by Svante Janson in 97 called the Gaussian Hilbert Spaces, where he sort of discussed this topic in great generality, and he realized that there's a generalization of U statistics, which are called generalized U statistics, where you allow not just dependence on random variables indexed by one index, but you can also allow pairwise indices. And in this case, the U's are our labels and the Y's are our edges. And you can represent subgraph densities in this manner. The key result is that such statistics allow for a Hoeffding type decomposition, except that it's more complicated. In a Hoeffding type decomposition, you sort of have a decomposition in terms of rates of, or rather orders of magnitude of fluctuation, and depending on whether your kernels are degenerate or not. And for this kind of general U statistics, in some sense it's similar, but it is still more complicated because the decomposition is more complicated. I will give an example. So let's take kappa to be this, what I think was called the bipodal graphon yesterday. And so we have alpha, beta, so essentially two groups. Gamma is the size of the first group. So we have alpha, beta, delta. This determines the connection probabilities. And if you take the edge density, very simple, you can decompose it in terms of random variables that I call V sub dot. This dot actually is a vertex. It's a subgraph of this edge. The trivial subgraph of this edge graph is just a vertex. So that's what this dot means. It's a trivial graph of size 1. That's one statistic that shows up. And there's another one which is V sub edge. Okay, that's a decomposition, and you can see this decomposition involves different rates. So here we have a constant. Okay, if you look at what n does, this is 1 over square root of n. This is 1 over n. This is 1 over n to the 3/2. And the same here, 1 over n to the 3. No, sorry, I got it. Yeah. Sorry, these two match. This is 1 over n. This is 1 over n, and this is 1 over n to the 3/2. So I've scaled things in such a way that V sub dot and V sub edge are centered, okay, and they have standard deviation of variance order 1. Okay, they're to be normalized, and there are parameters in here, row 1 and row 2. They are explicit because here we have an explicit graphon with a simple structure, and here are these two statistics. Okay, so now what are these statistics? The V dot is just involving the vertex labels. What we're essentially doing is we're counting the number of vertices in group 1, right? That's just the indicator that ui is less than gamma, centered. So that's just counting how many of the labels are in group 1, okay? And V sub edge is a centered subgraph count. What we're doing is we're centering, but pay attention to the fact that the centering is conditional on the vertex labels. It's not an overall centering, it's a centering conditional on the vertex label. That's important. Okay. So in sub,
there's no conditioning.
Pardon? Sorry, it is, well, there's a randomness in the centering. The random.
But there's no randomness in the centering for V dot.
That's right. Yes. Yes. So because it's in some sense conditional on the. You're right. You're quite right. In that sense, this is not a conditional center. Yes. The for this trivial one, with the V sub dot, there is no conditional, but for the others, it's all conditional on the vertex labels. Okay, so what in principle Boscher was looking at is that the question on the which conditions, what is sort of the leading term in this decomposition, right? If you look at this, you can tell now, well, if rho 1 is non-zero, that'll be the leading term. It'll be order 1 over square root of n, right? That determines the fluctuations because these are all smaller order. If rho 1 is 0, it'll be the next two terms that determine the limiting behavior. And you can see that you can read it off. Well, you know what v sub dot, that's just a sum of IID random variables, so that'll be a central limit theorem. So this converges to a normal. This one, you can make an educated guess. It's not quite IID because there's random centering in here, but you can make an educated guess that it'll be Gaussian as well. So ultimately what you have here, if rho 1 is non-zero, we have a Gaussian limit. If it's 0, we have a limit that is a sum of a chi-square and a normal distribution. That's exactly what Boscher did yesterday in more generality for more general graphons. Okay. If you don't believe me, because when I did this calculation by hand, that's sort of weird that this T sub h, it's sort of a sum of a few mixed binomial distributions. Ultimately, that's what it is. The mixture coming from how many vertices are, how many labels are in here, how many labels are in there. So if you don't believe me, here's some example. That's the case where rho 1 is non-zero, looks very Gaussian. And as soon as rho is 0, you start to see the deviation from Gaussian distribution. The scaling is different as well. And you see the chi-square coming in here, it makes this whole thing asymmetric. It's sort of counterintuitive. So what does it look like for triangles? The decomposition becomes more complicated. I've written it down here in terms of decreasing orders of magnitude of fluctuation. So R0 is just the expectation. And then we have different orders of magnitude of fluctuation. And you'll see this picture here. So there's again the familiar statistics v sub dot. Okay. But there's new statistics showing up. V sub triangle, v sub 2 star. What are these? Well, again, they are sums involving the centered indicators. That's already we have that before. But we have now new statistics, which are of this form, for example. V sub triangle is what I call a centered triangle count. So it is, again, the product of these three random variables, but is now the centered edge indicators. Okay, and the centering is done conditional on the labels. Okay, and again, Boscher's question generally is, what are these constants? Okay, now in this case, I give you what the constants are exactly because the underlying graphon is a 2x2 block graphon, right? Very simple. I can do the calculations explicitly. But in general, the question is far from obvious what these constants are. And in this case, it's also, we have just one chi-square. But in general, for a general graphon, like a smooth graphon, not of block matrix, block form, you may have an infinite sum of chi-squares. So this is far from trivial in general. So what we are proposing then, pardon?
Do you have different scale? How do scales?
How many do you have? I think that depends.
So how many scales do you have?
Yes, I think that depends on the size of the graph. So the larger the subgraph is you're counting, the further down you go in the decomposition. But at some point it stops. So this is the full decomposition for triangles. It doesn't go finer than that. So it doesn't. There's no finer fluctuations beyond this 1 over n to the 2.5.
Adrian, if you were to prove fluctuation theorems conditionally on the use, you can also read off from this, which would be the first term that would be fluctuating,
You
right?
should be able to do that, yes.
I guess that's the first term that has a y hat in it.
Yes, that's right. That's right. So it'll be this case.
It's not that one.
This is not random. So this not random, but there's more terms here that involve the v sub edges and things like that. You're so quite right. Yes, you can read it off from here in principle.
And would that be an interesting question?
I guess it would be, except that we took a different path, which is instead of looking at the subgraph densities, what we're proposing is, why don't we just look at these V's? as the fundamental statistics. Okay, the centered subgraph counts are the fundamental statistics. That's our proposal. Okay, so these are the statistics we're looking at. Now, a little caveat, maybe you see that some of these V's have prefactors. These prefactors may depend on the labels. Okay, they could be constants, but they could also be depending on the vertex labels. Okay, sometimes there's stuff here, sometimes there isn't. Okay, this one, the V subtriangle, is just a clean centered triangle count, whereas others have these prefactors. These prefactors involve the vertex labels, which we maybe don't want to test. We are interested in the edges. So what we propose is to take just these without these prefactors. Okay, so there's no prefactor here. So it's just a clean centered subgraph density. Okay, so what Janson and Nowitzki and Janson in his monograph showed was essentially that all these statistics converge jointly to a Gaussian distribution, to a multivariate Gaussian distribution. So what we've added to that story is a rate of convergence using Stein's method, which required the whole development of Stein's method, because these are sums of uncorrelated random variables, but they're still dependent. Why are they uncorrelated? Well, you can read it off. If you take, so this is a sum. If you take any of these, two of these, and you take the product of them, okay, as soon as there's one free edge, it doesn't occur twice, which is the case for any summand that is different, any combination of indices that is different. You take two of them, you multiply, there will be always at least one free edge. And then you take expectation, well, that's just zero because that's standard condition on the use, okay? And you only get a non-zero value if you take the same indices twice, each edge appears twice. Even then, the variance is straightforward to calculate. Because conditional on the vertex labels, the edges are still independent. Okay.
So, given a graph, how do you actually compute this if you don't know? Oh, sorry. If you don't know, if you don't know kappa and the labels, how do you actually compute this?
Excellent question. That'll be the topic of the second half of this talk. Exactly. So let's look at statistical applications. So what do you do in practice? Okay. As I said, the number one is we don't need these prefactors. Okay, we're not interested in the vertex labels, so that we just ignore those. If you want to understand the fluctuations of the subgraph densities, the classical ones, you need those as well. And we can prove, I mean, our Janson's and Nowitzki's and our limit theorems hold for all of these jointly. So any one you give to me, they jointly converge to Gaussian. So that's not the restriction here. It's just when you do actual statistics, you don't want to have these prefactors. There's no need for that. So we just take the clean ones. Okay, so statistical applications number one, let's work with the normalized one. So instead of normalizing by the prefactors I have here, to make it order one, why don't we just divide by the variance, which I can calculate explicitly? Well, that's just the variance of this sum is just the sum of the variances because they're uncorrelated, right? So just divide by that. And the variance of these guys are easy to calculate. Okay, that's just the variance of a binomial, very straightforward. The PIJ are the edge probabilities. Okay, and now if you use it as a test statistic, yes.
But in your setting, the PAI, AJs are actually random variables.
Okay, next slide.
Okay.
So if you set as a test statistic, the choices of F will determine what your test is sensitive to, right? But so you're quite right. In practice, the PIJ are known. So you have to replace them by P hat IJ. So that's an estimate of the edge probability between I and J. And then that's the actual test statistic is exactly what you said. You replace the PIJs by PI hat. Okay. So that's the test statistic. Now, where do the PIJ come from? Well, you run a random graph model fitting algorithm. You have, let's say, a stochastic block model, right? You have to cluster the vertices into classes, and then you estimate the connection probabilities, and that'll ultimately give you a PIJ. And you're right, the PIJ hats depend on the Y's, and so that's exactly what we're trying to analyze in this project with my PhD student. does the central limit theorem still hold for those statistics or statistics where the PIJs depend on the graph itself? So let me talk a little bit about interpretation. Now there's a downside to the story of nothing is for free, and including here, the interpretation of these statistics becomes more tricky because they're not subgraph densities, they're centered subgraph densities. So how do we interpret these? Now this one is sort of straightforward, right? If your z hat sub edge is large, that means you have more edges than you would expect. Well, that's straightforward to interpret. No problems there. Let's say z hat sub 2 star. How to interpret that? How can that value be large? Well, there's two ways to get that. One is you have too many 2 stars, right? In that case, the two indicators are larger than the expectation, and you get a positive value. But there's another way, which is both are zero, they're non-existent, in which case you have two negative values multiplied with each other, you get a positive value again. So this z value is large if you have either too many 2 stars or a lack of 2 stars, okay? So the interpretation becomes more difficult. Triangles, again, what does it mean to have a large value for this statistic? It means you have either too many triangles, that will give you a positive value, or you have the situation where you have too often, or more often than you would expect, you have that one edge is on and the other two are off, okay? That'll also give you a positive value, okay? So let's do a simulation study and see how these things behave in practice. So kappa here is a stochastic block model with 4 groups, and these are the connection probabilities. They're just random values we've chosen. Of course, it's symmetric. And we look at n equals 200 vertices. Now what we've done, you simulate this graph, okay? And then you reconstruct the community labels. Maybe we did in this project that was with Gaussian, we just said, well, let's just take an off-the-shelf algorithm in R that does that for us. And we took the variational EM algorithm from this package block models, which does the clustering and the estimation of the probabilities for us at the, that's a one-liner that does everything. And so we wanted to see how these things behave. And here are the results. So what am I reporting now? What you see here, let's just focus, let's say, on column 2, okay? Column 2 means the algorithm has, I told the algorithm to fit two communities, okay? So the algorithm will find 2 communities that it thinks are suitable for a 2x2 stochastic block model. And then it estimated the connection probabilities. Once I had that, I calculated these statistics, and here they are. These are the values of the statistics, okay? If the estimated 2x2 block model were the correct one, or close to the correct one, I would expect these values to be close to Gaussian, okay? Which are not quite, because they're a little bit too large. Remember, they're standard Gaussian, so 1.96 roughly should be the 95% upper and lower bound. So this will be too large. But as you see, if we go towards the correct value 4, because that's what we started with, now you can see these values are all within what you would expect for a standard Gaussian. And they're independent. So there's no, in the limit, if that's on the null hypothesis, they're also independent of each other. So they're very easy to interpret. Okay, black is the column that the algorithm gave us back and said, well, the algorithm believes black is the correct number, which is correct. 4 was the underlying correct number. And so everything is fine. This is a consistent picture for the simulation study, where we know the ground truth. Any questions so far? I haven't shown yet that if Remco is asking, well, you haven't shown that Z hat is Gaussian or that they are independent. I haven't shown that yet. At this point of the project, it was just a simulation study. Okay.
But also, I mean, if you were to do this in practice, right?
Yep.
So you
here,
see that
this is in practice, because that's an actual network.
Yeah, no, I was just thinking about the simulations. I still call it practice. I'm a probabilist. Who cares? So the first 3 you're going to be rejecting, but it's a multiple testing hypothesis, right? So if you're,
yeah, you're right.
So
you're absolutely right. So if you want to do that,
they're independent, so you can still do that. So the 4th one is the first one that you would not reject.
Correct.
But then you could go higher up, right? So would you take the first block size where you don't reject your null
That's what I would
hypothesis?
choose. Yeah, if I were a statistician, which I'm not, I'm a probabilist as well. So if I were a statistician,
we can talk to each other.
You're right. So you would do this and then stop at the point where the statistic no longer becomes significantly away from what you hypothesize it should be under the null hypothesis. But you're right. There's a multiple testing problem here that you would have to take care of, and so on and so forth. Of course, for 1 up to 3, these values have no reason to be independent because the null hypothesis is wrong. It is not a 3 by 3 or 2 by 2. Okay. From here onwards, they're sort of independent. If we can extend the theory to replacing the Pij's by Pij hats, and it's still Gaussian and independent in the limit. So here's a real example.
Is that obvious?
No, we have to prove it. We have to prove it.
Because if you have more groups, and it may be that you're somehow splitting them in a bad way.
Okay, let me backtrack on the statement.
Okay,
it is not obvious. It seems plausible, but not obvious. You're right. Okay, so this is a real network, 75 participants. This was data taken in a hospital in 2010 in France. In hospitals, 75 participants, that was nurses, doctors, patients were wearing these sensors, and they would record when people are near each other for a certain while. And so what we do is, I mean, the data set consists of all the encounters, and we just say, okay, 2 people are connected if they ever encountered each other during this 3-day period of observation. So, okay, so we ran the algorithm. Here's the multiple, so the different groups that you need if you fit the stochastic block model. And black is again what the algorithm gave us back to be the correct number. So now we can do diagnostics, okay? We can say, okay, let's look at how this model performs in terms of representing local graph statistics. And you can see it doesn't perform well, okay? In particular cycles, just look at this, the cycle, the 4 cycles, the 3 cycles, they're sort of off, as well as stars, okay? I'm not saying there are too many 4 cycles. There's something wrong with the 4 cycle structure. Now I have to think about how do you get a large value for Z? Well, too many 4 cycles is one way to get it, but it could also be 2 on, 2 off. That's also a way you get a positive value, okay? But that's a sort of a next, that we're not there yet in terms of, okay, let's do like routine statistical analysis of this data. In what ways you need to interpret these things. I mean, that we're not there yet. This is just sort of the first step towards that goal. Okay, so even if you fit 8 groups, it doesn't really match. So the takeaway here is this data is not well reflected by stochastic block model. That's what that would mean, at least from the perspective of local statistics. Okay, some theoretical properties, and now we're coming back to the p hat. Okay, so we thought, okay, let's start simple. So we let's assume you have a k by k stochastic block model, and let's assume the labels are known. Okay, then we can calculate the MLE estimator. Sorry, the E already stands for estimator. The maximum likelihood estimator of the edge densities is straightforward because it's just a binomial distribution. If the number of edges between 2 groups is binomial, and so the MLE estimator is just the ratio of edges versus the maximum number of edges you could have. So in that sense, the estimator is explicit. As a side note, if you do that, the edges are always perfectly matched. Okay, if that's your estimator, your Z sub edge statistic will be 0. So we'll not have a Gaussian limit. Okay, so what we have shown, that's the follow-up work, is that if you fix your F, okay, these statistics now have a slight bias that comes from the dependence in your PIs, PI hats. They're dependent on the edges weakly, but they are dependent. And there is a bias as a result. And here's the bias. It depends on F. So the worst case is the 2 star, which has a bias of 1 over square root of n, which sounds not too bad. But if your graph is like 200 or a few hundred, the constant is not small, but maybe 10 or something. It starts to influence your statistic. If you do, well, we see that it'll influence your statistic. So it's an important finding that to exclude your 2 star statistic if your graph is not too large. So here's an example. I've simulated this I don't remember what it was. I think it was the one from before this K that I showed you, this 4x4 graphon. This is a realization of that. I think 800 realizations. So each dot is the realization of one graph. I don't remember what the size of the graph was. N, the number of vertices. I don't remember. A few hundred. You can see they are, at least on the bivariate picture, they're all very Gaussian. But you can see that the two, of course, the edges is just 0, right? That's what I just said. The 2 stars statistic is slightly biased to the left. And if you take the average here over all these 2-star statistics, you can see there's a bias of minus 0.25. The other statistics are more or less okay, they're close to 0, but that one is clearly biased enough to be concerned about it. Okay, so we went one step further and said, well, let's look at, on top of that, now let's do the clustering, finding community labels, and we just said, okay, let's take an off-the-shelf algorithm, in this case, spectral clustering, that gives us the community labels. And then on top of that, we do the MLE to estimate the connection probabilities and see what's happening. And we've tested various models. We found that the spectral clustering doesn't seem to be performing well on the core periphery structure, which means you have part of the graph is dense, highly connected, and there is a periphery which is less connected. Of course, in the dense setting, everything is dense. But
so what's your spectral clustering? Is that
okay? So
hierarchical, but
are you asking me the details about the implementation of this?
I'm asking what the spectral clustering is, because there could be you look at sort of 4 eigenvectors and just use them to cluster, or you could look at just the top 2 eigenvectors, a second eigenvector split in half and again split in half in a second step.
So that's a good question. I don't remember the details. So we're taking let's say you want to find K communities, you take the top K eigenvectors and use those as a basis for clustering. So you take a K mean clustering or something of that sort. I don't remember the details, to be honest. We try to be off the shelf in the sense this is fairly standard. There's nothing fancy here. So I know there's a lot of embellishments of these algorithms. It might well be that certain types of embellishments works in this case well, but the ones that we've used off the shelf seem to have problem with the core periphery structure if the graph has this kind of structure. Yes. So we considered 3 regimes. Yes.
Sorry, I'm not sure I understand what you just said. Are you generating data using some kind of a model where core periphery is the...
No, sorry. Let me be clear. The underlying model is still the same graphon model. Okay. By core periphery means I've chosen the values here in such a way that we have highly connected, 0.8, highly connected, 0.8, that's 2 cores. And then we have 2 communities, which are not really communities. They have an inside and within the community connectivity of 0.1. Okay, but they're highly connected to this core. Okay, and we have 2 of these. Okay, now we're still in a dense setting. In some sense, they're still all dense, but the structure, I mean,
I understand.
Okay, you can't. This is not really a community because they're more connected to this community than they're connected among each other. So that's what makes this what's called a core periphery structure.
And that's why spectral clustering might not find these correctly.
Yes, I agree with that. But if you don't know the graph in advance, you wouldn't be able to tell. That's the issue, right? But I mean, it's being used for stochastic block model clustering, so it's not something that is out of the ordinary. So we've looked at 3 cases: the dense case, which is that's the graphon given by these connection probabilities. We have an intermediate and a somewhat more sparse case where we divide the probabilities by n with various powers to sort of see how these things perform in the non-dense case. The test statistic is just when you take these statistics here. Have I already shown that these things, have I mentioned that they converge to a Gaussian? Have I mentioned that? Yes. Okay, sorry, I forgot to say that they're biased a little bit, but I forgot to say that they're still multivariate Gaussian and independent in the limit. So the dependence is not strong enough to screw things up too much under these MLE estimators. Okay. Except that the true star statistic is biased, so we exclude that. Okay. So we calculate the chi-square statistic, which is the square of these three centered subgraph densities. Okay, we've excluded the 2 star because I said it's too biased for the number of vertices we're looking at. And if you assume the null hypothesis is true, that means if you assume that these are independent Gaussians, then the chi-square statistic should have a distribution which is chi-square with 5 degrees of freedom. And from that, you can calculate the p-value. So what we did, we calculated a bunch of p-values using this. And if the null hypothesis is true, these p-values should be uniformly distributed on the unit interval. If they're not, they're probably biased towards 0. Okay, so let's quickly look at how this spectral clustering algorithm performs. If you have enough vertices, it still performs well. So what we're reporting here is the number of correctly identified, correctly labeled vertices. If you see, for example, n is 800, then spectral clustering still performs okay, right? 99% of the vertices are correctly classified. Of course, if you go to the sparse regime, where you have fewer edges, you have loss of information, and therefore you would expect that your classification problem becomes harder. 0.25 is the lower bound. That's just random guess because we have 4 communities, right? So lower bound is 0.25. And of course, if you have fewer vertices, you also have a loss of information. But in general, spectral clustering can solve the job if you have enough vertices. So this is, okay, what we've looked at here is I'm not sure I have enough time. This is sort of 40 minutes now, so maybe give you a few more minutes. So here we're measuring how far away the p-value is from a uniform distribution. We just take the L1 distance of the cumulative distribution function of the p-values, which is just the area between the empirical cumulative distribution function and the straight line from 0 to 1. Okay. And so if you know the labels, if you know the underlying probabilities, that's the sort of, you know everything, then this value should be small because your p-values are close to the diagonal. I mean, the CDF are close to the diagonal. That means you're roughly uniformly distributed. That's all fine. If I know the labels, but I don't know the probabilities, that means I estimate those. You will expect some loss of precision, which is correct here. As you can see, they're still small, they're a bit larger because you have a bit more fluctuation, a bit more uncertainty. And then you use spectral clustering on top of that, you see suddenly things become much worse. That means in many cases, the p-values are way too small. That's the reason why you have these values close to 1. That means the p-values are essentially, many of them are 0, and then you have, so it means your empirical CDF goes up and then stays close to 1. So that'll give you, well, this is 2 times that distance. So that's the worst you can have is a half, but then you multiply by 2, you get 1 as the maximum worst case value. So we try to understand why is that? Why is, yes.
On the previous slide, I mean, going from n equals 200 up to 800, for the first 2 rows, labels and canon, and also the second row, like the middle value in the intermediate case is always decreasing. Is there any intuitive reason why the spectral clustering?
From here to here to here? Or you mean from here to here to here?
Yeah, from like 0.98 to 0.77, it's decreasing. Like is it?
Here it's increasing, right? Here,
yeah, it's always decreasing for the.
I think for the sparse one it's increasing, so you gain. But for the intermediate, it's increasing. That's fine. For the dense one, it's decreasing, right? It goes from 1 point to 0.88. I think the reason being is that if it gets it wrong quite badly. So if the p-value is off, it'll be just very close to 0. And that's why you get these. I'm not 100% sure. We haven't done a very rigorous analysis. It's sort of what my students sent me within the last week. So that's the state of analysis. So what we've done here is extracted some cases where the algorithm is doing well in general. So here is the correctly classified number of vertices from the spectral clustering. As you can see, everything is correctly classified. And then you expect these values to be like independent Gaussians, which they are, okay? Here is a situation where you get one wrong, one out of, I think this is 800. So 1 out of 800 is wrongly classified. And suddenly you can see that these statistics detect that, okay? And if you calculate the p-value out of this, of course, it's going to be essentially 0, okay? Because the this is very far away from 0. That's why you get these very extreme deviations for the p-value. What I like about this is the following. Number one, the centered subgraph densities detect this. Okay, they can see that only one has been wrongly classified. Not only that, it tells you something about the structural problem. When you look at which values are large, it's the stars that are large. Okay, and that's exactly what you would expect in a core periphery structure, that you have a lot of these stars. Okay, so stars play an important role in that model. And you can see that 2 star, 3 star, 4 star. These are the large values. The cycles are essentially unaffected. You can see the cycles are still fine. There's nothing wrong with the cycles. Okay. Even this one with a little appendix, which is sort of, it has a little bit of a star structure. Even that one is okay. All right. That's why, I mean, you can see from here, in some sense, it tells you something about the structural issues where the fit went wrong. Okay. What we also did later on is that, okay, can we then use this subgraph density idea to improve the clustering? So we did that. So we have, I don't remember what the details here were, what n is, but it's again 4 by 4. We have this core periphery structure. We calculate the chi-square statistic for different group sizes. And these are the chi-square values. As you can see, they're all essentially, you can tell that the model doesn't fit either way. So what you can do then is you take this as an input and see whether can we switch some of the class labels to improve the chi-square statistics, so to improve on the clustering, to better reflect the local structure. And if you do that, so here, by the way, the correctly classified number is 83%, correctly classified for this case, 4 by 4, because that's the ground truth. There we can calculate how many have been correctly classified. If you run an algorithm that sort of greedily reassigns labels to reduce the chi-square statistic, and you do that stepwise until you cannot improve any further, that's the picture. Of course, one class has nothing to do because it's just one class. Everyone has the same label, right? Nothing improvement here, of course. But when you go down, you suddenly see that there's a big jump from 3 to 4, was an indication that the subgraph statistics can pick up what the correct number should be for this model, okay? And then we can, of course, improve further. This is still significant. So you have to go further to like maybe you would choose 5 or 6 groups to properly hope that.
I would love to ask more questions, but actually I have to speak up to tell you that you should.
All right. So yeah, okay. So pros and cons. They're easy to calculate in general. It can be used for testing, proper testing, because you can calculate p-values. You can use them for clustering. The downside is, if you will, you need these values, these estimated values, and they can be more computationally expensive to calculate than the regular subgraph count statistics in the sparse case, at least. And the interpretation is, of course, not as straightforward, because now you have to think about what does a large z value for triangles mean. You have to think about that a bit more carefully. Okay, thank you very much. Apologies for the overtime.
That's fine. So maybe while the next speaker sets up, you can take a few more questions.
Yes.
Oh, Peter just doesn't need to set up. He just will speak extemporaneously from the back.
Right.
So
I have a
Okay, your question.
Yeah.
Okay, this is the question.
Yes.
So for the asymptotic result that you mentioned, so you mentioned that you use some Stein's method. So are there like finite finite guarantees for that result?
Yeah, it's a finite sample result.
Okay. Okay, so there are explicit guarantees that depend on W.
Depend on the graphon?
Yeah.
Yes.
Or kappa in your
Yes,
case.
yes.
Yeah.
Yes.
So our next speaker will be Peter, originally from Germany, then from New York, and now